Section C, the turning Earth.
So we all know the Earth revolves, right? Well, how do we prove it?
An easy way is to use a thing called a Foucault's pendulum.
Imagine going to the North Pole and setting up a frame like this. From the middle of the frame, directly above the pole, we hang a pendulum. Now we start the pendulum swinging and mark the place on the ground that the pendulum swings over. And then we look at the sky to see what star the pendulum is swinging towards. If we leave and come back in 3 hours, the pendulum isn't swinging over the same spot that we marked on the ground. But if we look at the sky, we see that the pendulum is still swinging toward the same star. The simplest and therefore the best explanation is that the Earth moved under the pendulum.
These big pendulums are called Foucault's pendulums. They're named after the guy who had the idea to make them.
Foucault's pendulums work anywhere on the Earth, but there's some really complicated trigonometry involved in explaining why they work all around the Earth. So we're not going to explain that. Just remember that Foucault's pendulums are proof of the rotation of the Earth.
Another proof of the Earth's rotation is this thing called the coriolis effect. The coriolis effect is the swirling of fluids like air and water that is caused by the rotation of the Earth. Sound complicated? It is.
Here, watch this planet. See how it turns? Okay, the circumference here at the equator is pretty big, and the circumference here up by Greenland is pretty small, but they rotate once around in the same exact amount of time. So, land by the equator is actually moving faster than Greenland.
Did you catch that? Qaqortoq, a town in Greenland, is up here. And if we look straight down below Qaqortoq to see what's on the equator, we find a little town in Brazil called Belém. Both Qaqortoq and Belém rotate once around the Earth every 24 hours. But Belém has farther to go, because the Earth is bigger around at the equator than it is up by Qaqortoq. So the land at the equator is actually moving faster than the land by Greenland.
Imagine you're at the equator in the suburbs of Belém. You fire a cannon due north toward Qaqortoq. As far as you can tell, the cannonball goes straight. But does it really?
To figure this out, we need to remember some physics. You fire the cannonball with a certain velocity due north toward the pole. But remember that you are also already moving east pretty fast, because at the equator you're moving really fast because of the rotation of the Earth. So the cannonball is moving north because you fired it that way. But looking from space, it's also moving east because you and the cannon were moving east when you fired it. Now remember, the higher latitudes are not moving as fast to the east as the equator because they don't have as far to go. But the cannonball keeps its initial eastward motion as it moves north. So the ground to the north won't be moving as fast eastward as the ball. From the ground, the ball is seen to start going north, but then curves toward the east as it travels north.
This curving toward the right works for any object moving over the northern hemisphere, air, water, clouds, whatever. In the southern hemisphere, the curve is in the opposite direction, to the left.
The Coriolis effect can explain how hurricanes and tornadoes spin. Hurricanes and tornadoes are low-pressure centers, which means that the air around them is moving in toward them. The right turning curl as the air moves in forms the swirl of the hurricane or tornado. If you're caught in a tornado that's spinning counterclockwise, you know you're in the northern hemisphere.